Hey everyone, Joel here. Hopefully this is the last part if things go according to plan. It should be. And just because I wanted to remind you, at Joel Grus. So last video I forgot to check it in at the end, so I did that off camera. But it's done. So let's make a branch for part 6, which I hope is the last part, and check out part of 6. Okay, so that's good. And if you remember, we had this simple learned function that we were working on, and we talked about a couple of things we wanted to improve. So one was to introduce a notion of a parameter. So from autograd.tensor import tensor. And a parameter is just going to be, let me go back to that simple learned function. I had to do this tensor where I initialize it with random variables, and I said it was requires grad. Well, I'm not going to force that, so I'm just saying parameter is going to be a subclass of tensor, and I'm actually going to initialize it with a shape, right? And what I'm going to do is I'm just going to call the superclass constructor, which is the parameter constructor. And the data, I'll do numpy, so I need to import that from numpy.random. No, that's not what I'm going to do at all. Import numpy as np. So let's just say data equals npy.random.randn shape. And then super.init data, and then requires grad equals true. So, in general, you wouldn't necessarily want to initialize your parameters with random normal. You might want to initialize them in other ways. We'll leave that as an exercise for the reader. And then the rest of it can just get implemented or just use all the tensors. So, let's export these at top level from autograd.tensor, import tensor, and from autograd.parameter, import parameter. So that should be fine. And I should write a test, but I'm not going to right now. So what I'm going to do is from autograd import tensor and parameter. And now what I'll do is I'll just say W is a parameter where I can specify the shape being 3. And B is a parameter where I give it no shape. And I think that will work. So, I basically said tensor with shape 3 requires grad true, random values, and so on. So now, if I do Python simple learn function.py, it still works. But now I have this slightly cleaner syntax for defining parameters. And parameters are tensors, but necessarily they require gradients, and necessarily they get started like that. So that's good. The second thing I said I wanted to do was, having to keep track of all the parameters manually was actually kind of a pain. So what I'm going to do is, again, I'm stealing, a lot of ideas from PyTorch, and so I'm going to steal another one and say class module. So from autograd.tensor import tensor. And so what is a module? A module is going to be basically a collection of parameters that has a forward method. So what do I want to do? I want to say parameters, and that's going to be just an iterator over parameter, and from Autograd parameter import parameter. So this is going to be another reason to use parameters, is that we're going to do this, and I'm going to use my friend the inspect module, and so I want to get all the parameters in the module. So I want to do a couple of things. For item in inspect got get members, it's for name value in inspect get members self. So I should put self here. And so what am I going to do? I'm going to say if is instance value parameter, just yield the value. So if it's a parameter, I'll yield it up. Otherwise, if it's a module, and that's so I can have nested nested modules, right? So I have a module and it belongs to another module. Then I'll look at its parameters. Yield from value dot parameters, and then otherwise I won't do anything else. So that's one thing I can do. And now I said, let me close this out. When I was looking here, that having to zero gradients was a pain, and so I'll just do that here. Def zero grad self for parameter in self dot parameters parameter dot zero grad. So now that I've put these in the module, and because we use this inspect magic, I don't have to be real explicit about how this is happening. And I'm just going to say actually, I take that back. I am yeah, I'll say forward. You know what? I'll leave that out. In PyTorch, their module says it has to have a forward. I'm going to punt on that, and ours will have one, but I don't see why I need to put that in the base class. So I'm actually not going to. A module can do anything. It just has some parameters, and it knows how to zero out its gradient. And so let's export that as well. Autograd.module, import module, so that's good. And so now what I want to do is I want to say, class my module, and in the constructor, I'm just going to say self.w equals this parameter, and I'll wipe that out. And then self.b is this parameter, and then I'll just call it predict self and inputs, which is tensor, and that's going to give me another tensor. And I'll say return inputs at self.w plus self.b. So that's good. And you know what, I'll call this model. That's easy enough. So I have this learning rate, I have this batch size, and now let's say a model is an instance of my model. And so what I can do is I can say, instead of having to worry about the parameters, I'll say model.zeroGrad, because I put that in the base class. I get inputs predicted equals model.predict inputs, actual errors, loss backwards, and now this It's really model.w minus equals model.b minus equals model.w.grad model.b.grad. So that may not feel that much cleaner, but to me it feels slightly cleaner. And so now if I run it again, I get an error that iterator is not defined, which is true, so I need to import that. Name module is not defined, so I better, I thought I imported that, I guess not. Okay, that's fine too. And now you can see it's doing the same thing basically, and it seemed like it was slightly slower because all this machinery we're adding, we're not exactly optimizing it, but it works. And now you'll notice that it's still a nuisance that I have to do this. So I can take care of that as well, and I'll do that by introducing an optimizer. So here's where optimizers go here. And you know, in an ideal world, I'd implement a base class optimizer with an interface and everything, but I'm just going to do stochastic gradient descent. So to initialize it, I'm just going to have the learning rate, let's say 0.1 is the default, self.lr equals lr, and then I'm going to do a step function that takes in a module. So from autograd.module import module. So step self, and let's say module, that's fine. And that's also going to return nothing. And so all I'll do is I'll say for parameter in module dot parameters, and you know, you can see where this is going. Parameter minus equal parameter dot grad times self dot learning rate. Okay. And so now if I go back to my simple learned function, I'll say, you know, from autograd.optimizer import SGD. And now I'll say optimizer equals SGD learning rate equals that. And that means that instead of doing that, I can just say optimizer.step model. And now I don't have to worry about that. And so you can see that, I've gotten to this nice place where if I define my model in this module here, whoops, that's not right. So I define some parameters, and I say this is a, you know, a three-dimensional parameter, this is a zero-dimensional parameter, and I write a function that basically says here's my computation. Then I can call ZeroGrad on the model itself, and that will automatically pass it on to all the parameters. Similarly, I can call the optimizer on the model itself, and that will handle all of this. So, and you can see that it still works, and it's still learning the function with no errors. And so this is almost what I need to do a neural net. And the last thing I need is I need an activation function. So let's go here and do another, call it func.py. I'll call it functions. Functions, that's fine. So from autograd.tensor import tensor, that's fine. What I want to do is I want to you know, define a tan-h function which takes some tensor, which is a tensor, and it returns another tensor. And so we're going to do basically the same thing we did when we were doing all the arithmetic operations, right? So import numpy as np. So data equals numpy.tanh of tensor data. So that's really easy. Requires grad equals tensor dot requires grad. And then if requires grad, depends on equals dependency tensor grad function. Otherwise depends on equals nothing. And then we can just return the tensor of data and requires grad and depends on. So that means I need to write, again, the grad function. So what is the grad function? Which is a numpy array and returns a numpy array. So if tanh has this nice feature where the derivative or the gradient is just 1 minus the outcome squared. So here we already have data, which is the output. So all I need to do is return grad times 1 minus data times data. And I think that's right. So I multiply the gradient component-wise by 1 minus data times data, and that happens to be the gradient for tanh. And so I think that's good. I don't, in an ideal world, again, I would write unit tests for this, but now I think I don't want to. So we have basically all the pieces we need to do, and you knew this was coming, to do Fizz Buzz. So let me copy this simple learn function because we can use a lot of its this from autograd.function import tanh. That should be good. So if you've seen new videos, you know that we learn Fizz Buzz by using a binary encoding, which takes an which takes a number and turns it into a list of 10 zeros and ones. So let's do from typing import list. And I will use my stupid bit arithmetic trick for I in range 10. So, for each number 0 to 10, I shift the bits that many to the right and AND it with 1. So that will just pull off the binary representation. And there's also the Fizz Buzz encode, which tells me which of the 4 classes it belongs to. We treat this as a 4-class classification problem. So this is by 15. We return the 4th class. Otherwise, if it's divisible by 5, I've done this so many times I can do it in my sleep, but haven't done it with my own Autograd library. So that's maybe the exciting part. It's exciting to me. And then finally, we return the 1st class, which means as is. So now we have, X train is a tensor of binary encode X for X in range 101, 1024. So we want to predict for, maybe some of you don't know what Fizz Buzz is, so let me tell you. I assume you do. For each number 1 to print the numbers 1 to 100, except the number is divisible by 3, print Fizz. The number is divisible by 5, print Buzz. And this is kind of, my calling card, although maybe hating notebooks is now my calling card. I have several calling cards. 15, print, Fizz Buzz. Okay, so that's what the problem is. And so X train and then Y train equals tensor of Fizz Buzz encode X for X in range 101, 10, 24. And that's it. And so now, you know, we can do Fizz Buzz model, I'll call it. And now this one will take a parameter, and it will be num hidden, which is an int, and I'll default it to 50 because that's what I like. And so, you know, self.w1 equals a parameter that's 10, because that's the input dimension, by num hidden. Self.b1 equals a parameter that's just num hidden. Self.w2 equals a parameter that's num hidden by 4. Self.b2 is a parameter that's just 4. And you know, one place you could take this even further is to say each of these is a dense, fully connected layer, so we can introduce a module that's a linear module, and then just say, you know, self.first module is a linear module from 10 to. But you know, this is showing you what the Autograd kind of buys you, which means you don't have to use those kind of modules. You can just so now our predict is going to have a couple of steps, and you know, inputs will be batch size by 10. So so I'll say you know, x1, these are terrible variable names, but equals inputs at self.w1 plus self.b1, and so that will be batch size by num hidden. Let me close this so I can see all this stuff. And then, you know, I'll want to use my activation layer, so x2 equals tanh of x1, and I never wrote a test for tanh, so it's possible I screwed it up and this won't work. And then x3 is going to be, you know, tanh x1. Tanh is not going to change the size, so it will also be batch size by num hidden. And so that means that x2 at self.w2 plus self.b2, and this will be batch size by 4, and then I'll just return x3. You know, sometimes you'll see it, they'll give it the same name each time. I don't really like doing that, but so here's my optimizer, here's my batch size. Model is Fizz Buzz model. So let's, you know, run this for range 10, epoch loss, model 0 grad, inputs equals x data. The only other thing I'll do is so I want to be able to take the so let me do this. Starts equals numpy dot a range 0 x train dot shape 0. So that'll be the first dimension, and then batch size. And you know, I can actually do that out here, and then in here I'll say numpy dot random dot shuffle starts, and then I can just do for start and start. So I'll get a different order each epoch, which is good. So I get the end, I zero out the gradient. I pull the inputs out, so that's x train start plus end predicted equals y train start to end, errors sum backwards, epoch loss, optimizer step data, print epoch loss. So let us run that for 10 epochs and see where it goes. name dependency is not defined. Okay, that's easy enough to fix. Dependency. I don't think I need anything else there. Okay, so that's good. It looks like it is training, which is nice. So let me, let me kick off an IPython and run it there, although it was running pretty slow. So let me give it 5,000 epochs, and that might take a really long time. Run fizzbuzz.py. So you can see that as it trains, the loss seems to be going down somewhat consistently. And you can also see that it's really slow. And I think most of that is due to the fact that the recording is taking up like all of my CPU. So, while we're doing that, let's figure out how to evaluate it. So now for x in range 1, 101, so that's 1 to 100, input equals, let's say, binary encode x, and let's wrap it in tensor. Predicted equals model.predict on inputs. So this should be 1 by 4. So I'll just pull it out like that. So then that's going to be 4. And let's say predicted index equals numpy dot argmax of predicted.data, which I can do. And then actual index equals numpy dot argmax of Fizz Buzz encode x. And then the labels will be, for class 0, it's just string x, fizz, buzz, and Fizz Buzz. And let's say num correct equals 0. So if predicted index equals actual index, num correct plus equals 1, and then print x labels predicted index and labels actual index. And then finally we'll print num correct out of 100. So let's go here, and this thing is taking quite a long time really, and that is because the stupid recording software is taking 500% of my CPU, which doesn't leave a lot for running my neural network, which is really kind of unfortunate. Part of me wants to stop this, but part of me wants to let it run for another, what did I give it, 5,000 epochs. Really, this model needs like 10,000 to train, so it's not going to train fully. I should probably figure out how to record things without using up so much CPU. But anyway, let us review what we've done. Keep in mind, this is all machinery that we've built, other than NumPy, which we are freeloading off of. But everything besides NumPy is machinery we've built. So we have this module class, and I have a module, I initialize it, and all I do is I assign it some parameters. And these parameters could be of arbitrary size. Here I used a matrix and a vector and a matrix and a vector. And then I define a predict function, which is really just doing arithmetic using these parameters. So I want to take my inputs and matrix multiply them by one parameter, add another parameter, call this tanh function, and do another. So basically, rather than having to learn some kind of convoluted syntax, I'm I'm really just working with these things the way I would work with variables in bare Python. And so that's the really nice feature of having a library like this, is that now I can, write out what I want to do in terms of Python math operations, and I get all the backpropagation and the gradient stuff for free. Not for free, because we had to, it took a lot of work to build that into the additions and the subtractions and the multiplications. But now when it's time to build and train a model, I get that for free. All I have to do is call Autograd on the model and call the optimizer on the model. And then in the training, I can not really worry about what's happening inside the model. I just know that because it's a module, it has that Autograd, and it can be operated on by an optimizer. And I know it has a predict method. I could probably should probably write a sum of squared errors function, and then I can not have to do all these steps and so on. So you can see that there's like a lot of ways to keep enhancing that. But I've kind of built the basics that I wanted to do, and satisfied my curiosity that I was able to build a system that does this, even though it's not that performant when I'm recording at the same time. But there's a sense in which it's, a degree harder than the kind of, okay, here's a layer, here's a layer, here's a layer. Now we can start doing things that are arbitrary computational graphs. And so we don't have to think in terms of layers and layers and layers, but we can build complicated things. We could introduce ifs and thens and so on, and really build complicated computational graphs and still backpropagate through them. So this finished with my 5,000 epochs. So let me do the moment of truth, and that result, that loss, it doesn't look that good to me, but that said, I got 100 out of 100 correct. So let me make sure I didn't cheat somehow. It's possible I cheated. So I take the x, I binary encode it, I turn it into a tensor. I call model predict on that thing and pull out the only row. The index is calling numpy argmax on the predicted data, so that's not cheating. The actual index is calling Fizz Buzz encode, which is kind of the ground truth, and taking its argmax and getting its label. So that's really nice, actually. So let's look at predicted. So that's for 100. So it's very low score there, very low score, very low score, and it picked. And let's print predicted there as well, and we can just see how those probabilities look. And that's not really easy reading, but put a lot in the first spot, put a lot in the first spot, put a lot in the second spot, put a bunch in the fourth spot. So it really okay. So it did a good job, even though I only trained it for half as long as I would have liked to. So I think I think that's really where I want to leave this. Module does most of what I want it to. You could obviously write a lot more functions than just tan-h, but tan-h is the only one that we need. You can implement more optimizers. You can implement a base class that says every optimizer has a step that looks like this. I didn't bother because there wasn't much point to it. If I were selling this as a product, I would probably write more unit tests because I didn't write enough unit tests. I think that's kind of it. So get add Autograd, get add simple learn function, get add Fizz Buzz. Am I in the right branch? Part of 6, that is the right branch, yeah. So get status, commit part 06, git push origin part 06. So, find me on Twitter at Joel Grus, and it's possible I'll do one more stupid video on the end. I haven't decided yet, but if I haven't, this is a good place to end. So thanks for watching, and let me know if you like this, if you didn't like this, and tell your friends. And it's been fun, and I will try and figure out how to record without taking up so much freaking CPU time. So I'll see you later.